All right, today we're going to talk about one of the most powerful and, honestly, one of the cleverest shortcuts in all of quantum mechanics. It's called the Born approximation. Let's get right into it. So, think about this. How do you actually see an atom? I mean, you can't just look at it. The way we do it is we throw something at it, maybe a neutron, maybe an electron, and we watch how it bounces off. This whole process is called scattering, and it's basically our only way of seeing things that are totally unseeable. But yeah, there's a big problem. So here's our game plan. First, we'll dig into why scattering is so incredibly hard to calculate. Then we'll meet the man of the hour, Max Born, and his brilliant shortcut. After that, we'll break down exactly how this approximation works, see all the amazing places it's being used today, and finally, we'll look at what happens when that first simple step just isn't quite enough. Okay, so let's jump into the main challenge here. Why is it so ridiculously hard to predict exactly how one tiny little thing is going to scatter off another? Scattering theory is a huge deal in physics. It's how we understand everything from the structure of an atom to the very core of our planet. But the equations, the math that actually describes it all, it's a total nightmare. Trying to solve them perfectly is, a lot of the time, just impossible. And here's why. It all comes down to this crazy mathematical feedback loop. Picture this. You've got a wave of energy coming in, and it hits an atom. That wave messes with the atom, right? But the atom's reaction, the way it gets pushed around or polarized, instantly creates its own field. And that new field immediately changes the very wave that's hitting it. So to calculate the final scattered wave, you need to already know what the final scattered wave is. It's a total chicken and egg problem. This is where a little bit of genius pragmatism saves the day. Back in the early Wild West days of quantum mechanics, a physicist named Max Born came up with a way to just slice right through this mathematical knot. The year was 1926. Born published a paper with this absolutely brilliant simplification. See, he wasn't trying to find the perfect, exact solution. He was trying to find a useful answer that was good enough. And his core idea was just beautifully simple. He basically asked, what if we just ignore that messy feedback loop? What if we just pretend the thing getting hit is so weak, so insignificant, that its reaction doesn't really change the original incoming wave at all? And this comparison just lays it all out perfectly. On the left, you've got the exact way, that self-referential headache we were talking about, and on the right, that's Born's shortcut. By just assuming the object's reaction is basically zero, we break the loop. We just say, you know what? The final scattered wave is decided only by that first clean, undisturbed incoming wave. It's an approximation, for sure, but man, is it a useful one. So let's take a closer look. How does this simple little idea become a tool that physicists are still using all the time, nearly a century later? Okay, here's the formal textbook definition. That incident field is just the initial wave you send in. The total field is that complicated mess that includes the scatterer's reaction. Born's idea is to just go into the equations and replace the complicated total field with the simple incident field. That's it. A really great way to picture this is with a simple analogy. Imagine you're shooting really powerful radio waves at a super flimsy styrofoam column. I mean, that styrofoam is barely going to affect those powerful waves, right? The waves that actually cause the scattering are, for all practical purposes, exactly the same as the original waves. The feedback is just so tiny you can totally ignore it. And here is where the real mathematical magic kicks in. When you make this simplification, that super complex scattering equation suddenly turns into something much, much more elegant, a Fourier transform. So what does that mean in plain English? It means the pattern of the scattered waves becomes a direct, readable map of the object that did the scattering. You're not just seeing a bounce anymore, you're basically seeing a blueprint. But, and this is a huge but, this shortcut has a very important rule. It only works if the approximation is actually valid, when the field created by the scatterer is way, way weaker than the original field you're hitting it with. It works great for our styrofoam column, but it would totally fail for a giant metal one. So, knowing that one condition, where can we actually use this idea from 1926? The answer, it turns out, is pretty much everywhere. Physicists use it all the time in neutron scattering experiments. It lets them map out the structure of materials, literally atom by atom, because the interaction is weak enough that this first approximation is almost always perfect. It's also critical in cutting-edge material science. For example, researchers use it to figure out how electrons scatter inside a sheet of graphene, and that's essential knowledge if you want to design next-generation electronics.
And that helps us calculate things like conductivity in really advanced materials, like bilayer graphene. The principles are just so foundational.
And just to show you the unbelievable scale of this idea, geophysicists use the exact same concept to study how seismic waves from earthquakes scatter as they travel through the Earth. It helps them map the structure of our planet's core. We're talking about scaling an idea from the size of an atom all the way up to the size of a planet. It's incredible. But what happens when that styrofoam column is actually a giant metal one? What do you do when the thing you're hitting isn't a small, weak perturbation? Well, physicists built an upgrade. Yeah, sometimes the object you're probing has a huge effect that you just can't ignore. Think about charged particles scattering off of other charged particles. The basic electrostatic force between them is a massive effect, not a tiny one. In cases like that, the simple Born approximation just falls apart. So they developed something called the distorted wave-borne approximation, or the DWBA. And it's a really clever multi-step process. First, you split the problem into a big, easy part you can solve perfectly and a smaller, hard part you can't. Second, you solve that easy part to figure out how it distorts the initial wave. And finally, you take that new, already distorted wave and you use that as the starting point for a regular Born approximation on the leftover hard part. It's like giving your approximation a much, much better head start. And this more powerful method is absolutely essential in a ton of fields. It's used to analyze nuclear reactions, to understand fundamental quantum processes like bremsstrom, that's the radiation you get when charged particles slow down, and the photoelectric effect. And it's all over the place in condensed matter research. And this really brings us back to the core idea, doesn't it? The Born approximation, in both its simple and its more advanced form, isn't just a tool for calculation. It's a philosophy. It's a way of finding a smart, elegant, and useful answer to a problem that might otherwise seem completely impossible. It really makes you wonder, what other scientific dead ends are just one clever shortcut away from a breakthrough?